Alright guys, let's get rolling on vodcast 5.1. We're going to talk about the periodic table. And really this is where we really start to get into some actual chemistry. We've done a little bit of calculations. We've talked a little bit about matter. But in this section is where, first off, obviously the periodic table is sort of like, the holy scriptures for chemistry. This is where we're going to find all the useful information that we're going to use and where we're going to find molar masses and all that stuff. But more to the point, we're going to talk in this section, not today, but in this unit about electrons. And electrons have everything to do with reactions. So that's pretty important to us. But to understand electrons, I think it helps a little bit to know a little bit about the periodic table. So first off, let's talk real briefly about the development of the periodic table. Like, where does the periodic table come from? How did we develop it? And those sorts of things. So first off, these are a list of guys who helped to develop the periodic table. So Lavoisier, he's a pretty famous guy in chemistry circles, and basically he's a guy that does the first list of the elements. Okay, he does a lot of other stuff. He talks about equilibrium, and he discovers a bunch of gases and all kinds of stuff. He's kind of a big guy in chemistry. He's one of those guys that's up for father of chemistry. But what really becomes important for us is that he comes up with the first sort of list of elements. And if I recall correctly, I think he had about 28 or maybe 47 elements at that time. Obviously, I hadn't discovered very many of them at that time. So the next guy to really start to organize these things was a guy named Dobereiner. As I recall, a German chemist. A lot of the early chemists are German. And he comes up with what are called triads. And these are basically groups of 3 elements that have very similar properties. And this is sort of the first real time that we're trying to classify the elements based on their properties, okay, and sort of group them together. So he gets a lot of credit for this idea. And just a couple of examples. So he put chlorine, bromine, and iodine in a group together. They had very similar properties to each other. He had lithium, sodium, and potassium all together in groups. And he had a couple other of these triads where he had 3, okay, elements grouped together according to their properties. Okay, the next guy is a French guy named Chancourtois. And I'm sure I'm totally butchering that, Chancourtois, even though I had 4 years of French. I'm sure I'm messing it up. But he's got like 8 names. This just happens to be his last one. But he actually is the first guy to notice something really important about the periodic table. He's the first guy to really notice something called periodicity. Okay? Now, what periodicity is periodicity is pretty much what it sounds like. It means that he notices that properties repeat themselves periodically. Okay? So, properties repeat periodically. Now, what does that mean? That means that, like, so every 8 elements or every, 15 elements or every 12 elements or something like that, that it's a consistent number. And we'll see that a lot of it has to do with 8 here in a little bit. But that the properties repeat themselves periodically. So you'd have sodium, and then you'd go through so many elements, and then you'd come back and you'd have potassium that had very similar properties. And so he's going to start to group these things together. In fact, he's one of the first guys to come up with what we might categorize as a periodic table. He comes up with sort of this weird spiral-looking thing that organizes the elements, but not really according to what we would recognize today. So he doesn't really get credit for making the first periodic table. The next guy is a guy named Newlands, and Newlands comes up with an idea called octaves. Now, if this sounds like something from music, it is. And essentially, he comes up with this idea that elements are repeating themselves. Okay, so back to this periodically idea. Elements are repeating themselves basically every 8 elements. Now, he kind of gets laughed at the time, but we'll see in a little bit that actually this idea has a lot more sense in it than you might initially think. There's a lot more to do with that idea of 8 than originally seems likely. Okay, so here's the first real periodic table. It's developed by a Russian guy named Mendeleev, or Mendeleev. Mendeleev is usually the way he's pronounced his name. He's a Russian scientist. We're talking about 1869 here. And what Mendeleev does, and it takes him a long time, and he's one of these really giants of science that doesn't get as much credit But I mean, this is a development like, Newton or Darwin or Einstein, really, being able to organize the elements. This is sort of his first, as he's working, making his first copy of the periodic table. It's kind of hard to read these, but you can sort of see that there's like this arrangement, that they're arranged in this very certain way. And if you look really close, and we'll try to zoom in here, but if you look really close, you can see that they're sort of arranged according to mass, that it's continually going up according to atomic mass. So this is sort of his notes copy, okay? And then his first actual copy that he publishes, you can tell that it's Russian because there's some good Cyrillic writing on it. This is like the first real copy that he publishes in a book about chemistry. And so you see them arranged in this ascending or going up order of atomic mass, okay? Additionally, and what makes it really mind-blowing about what Mendeleev does is he not only arranges it according to atomic mass, but perhaps just as important, he arranges them according to properties, okay? So if we look at a particular row here, we've got like fluorine, chlorine, bromine, and iodine. Those things all behave very similarly. They're very reactive. They form a lot of the same compounds, and so Mendeleev arranged them in these rows of similar properties. So not just by mass, but also by similar properties. He noticed the same thing was true of nitrogen and phosphorus and all these other elements here. And then some of the other elements that we would know a lot, so like lithium, sodium, rubidium, cesium, okay? And again, this has a lot to do, if you look back to the triads, the Dobereiner came up with lithium, sodium, potassium, chlorine, bromine, iodine. Okay, these same sort of scenarios are coming up again and again, that these elements have very similar properties, okay? So one thing that Mendeleev does notice, though, is that there are some flaws in his table. One of the big ones is right here, okay? He's trying to arrange everything according to atomic mass as it's increasing, but you see here, what you've got here is 122, okay, and then 128 and 127, and then 123. Iodine's kind of out of order here. Now, Mendeleev knows that he should arrange his table according to properties, and he knows that mass has something to do with it, but he notices these exceptions in here where sometimes the mass is a little out of order according to what it sort of should be. Mass-wise, iodine should be up here, but he knows that iodine belongs with bromine and chlorine, that it has similar properties to them. So Mendeleev basically says, hey, this is what it is. I'm not real sure why this works out this way, but perhaps someone will figure this out some point down the line. And in fact, they're going to, and we'll talk about that here in a second. Another cool thing about Mendeleev's table that was very untrue of the other guys that started to come up with these ideas is that Mendeleev actually predicts elements that they haven't discovered at the time. So we see a question mark here. He's going to predict what those are. And he actually gives them names. He calls this Eka aluminum, Eka silicon. Eka is the Sanskrit word that means beyond, so it's like past aluminum. And this we know today as gallium. And so he's accurately predicting elements in the future. In fact, he was so accurate in his predictions that he even got the masses basically right, even though they hadn't discovered it yet. He was so accurate with it that later on, when a guy is discovering some of these elements, when the guy that discovers gallium discovers it, he gives it a mass, and Mendeleev basically writes back and publishes a paper that says this guy's wrong, even though the guy that discovered it was actually an experimental guy, and Mendeleev was just a theorist, meaning that he didn't really run the experiments. He just said this is the way it should be. And it turns out that Mendeleev was right. He was kind of a prima donna, but I mean, when you're right, you're right, and so he was. So I mean, he gets the main credit. There's another guy named Meyer that comes up with the periodic table about the same time as Mendeleev, but Mendeleev basically gets pretty much all the credit for it in most cases. So what are the big points about Mendeleev's? Okay, so Mendeleev's table is arranged according to mass. Okay. Now Mendeleev doesn't know about isotopes. No one does at this point, so they're just sort of working on the masses that they know. And you see, if you looked at the table there were a couple of decimals, so they kind of knew that something was fishy there, but they're arranged according to mass. And okay, properties. Okay, and by properties we mean both physical and chemical. Okay, more importantly chemically, but the physical ones as well. Okay, so Mendeleev arranges his table according to that. And so the flaws are, remember that he notices that the masses are out of order sometimes. Okay, so they got to find some way to fix that idea that the masses are out of order. Well, the guy that does that is a guy named Henry Mosley. And Mosley's contribution is that he arranges the table. Okay, so he takes Mendeleev's table, nothing new. I mean, he's got Mendeleev's table. He's not really coming up with one on his own. But he arranges the table according to, okay, atomic number. Now, why is this so important? Well, first off, this is the way that the table is arranged today. The table is arranged today according to increasing atomic number, not according to mass. The mass works most of the time, but again, just like in Mendeleev's table, there are occasionally some inconsistencies there. So the atomic number works all the way across. Mosley also left some holes in his table for technetium and promethium. He figured that they would be discovered, and they were eventually. They don't exist in nature. They had to be man-made, and they're radioactive. But he accurately predicts those atomic numbers. So these are the guys that lead up to the modern periodic table. Basically, when Mosley assembles his table, we have a table that looks pretty similar to what we have today. They've discovered stuff that Mendeleev didn't know about, like he didn't know about noble gases. They added that stuff on, and then arranging everything according to atomic numbers instead of mass. So basically sorts out all the errors. It puts the iodines where they should be, and it puts the argon and the potassium and all that stuff in their proper places. Okay, so that's pretty much it for the development of the periodic table. And I want to real briefly talk about a little bit about looking at the periodic table and sort of seeing where parts are on the table and what they're called and how we name those things and all of that fun and exciting stuff. So this is ptable.com, okay? And if you go there, you'll sort of immediately notice that the table is color-coded, and it's color-coded in very specific ways. And you need to make these notes either in your notes or on a periodic table so that you know what these groups are called. So the first thing that I want to do is just sort of real quick is let you know that if you look off to the side, right here, there is like a staircase right here on the periodic table. Okay? Whoops. ptable.com is really awesome. You can pull up all kinds of cool stuff. But if you look right in this general area here, okay, you'll note that there's like this little staircase here, and we can actually draw a staircase. In fact, I think there is one in your periodic table. If you draw it underneath boron and then just sort of keep going down one step at a time through the elements here, you'll see the staircase. Now, here's the way it works. Everything that touches that staircase is called a metalloid. Okay? Everything to the left of that staircase, okay, so from here, oh, not again, from all this area here over all of this and the stuff that's down on the bottom that we're not really talking about right now, okay, and we'll get to in a little bit, this stuff down here, those are all what we call metals. So if you look at the staircase there, everything to the left of the staircase is a metal. Everything that touches the staircase or is part of the staircase is what we call a metalloid. Okay, metalloid. And then everything to the right of the staircase is a non-metal. Now, you'll notice that that's not a lot. I mean, it's like, you know, this little green group here, group 17, the halogens, and then the noble gases over here. So it's not a whole lot, but it's really important. There are millions and millions of compounds that are basically made up of just the non-metals. Okay, so that's pretty important. So that's sort of classification system number one. The second way, and again, this is real easy to see on ptable.com, but the other categories are alkali metals, okay, so group 1 on the periodic table, okay, the orange stuff over there, those are, whoops, and again, I'm just going to keep pulling up elements, apparently one after another. Okay, the orange ones are the alkali metals, okay, the next group over, the yellow ones now, are the alkali earth metals, okay. If we look down at the bottom of the table, okay, the part that we don't look at all that often, we've got lanthanoids, or sometimes they're called lanthanides. And then the very bottom row, down here, these are the actinoids or actinides. Either way is fine. And remember, we sort of briefly went over this before, but these rows actually slide up in here. We can make the periodic table if we hit wide. If you go to ptable.com and hit wide, it's going to put those in where they should actually go. Okay, right in there. So that's This row then are the lanthanoids, okay, and then the actinoids. We don't usually put them there because it makes the table really wide. You can't really see everything, so we like to spread it back out. Okay. The other super important groups here are the halogens. Okay, group 17. Okay, over here. You are going to see a lot of the halogens. Okay, so you need to know what those are. And then the noble gases are the very last column. They're called noble gases because they don't really like to react with other things. They're kind of like held above. They were at one point called the inert gases because they don't like to react very much, and that's why it took so long to discover them. That's why Mendeleev and his crew didn't know anything about them at the time. Okay, so you want to make sure that you know all of those categories real quick. So let's just real briefly run through those again and just sort of make a few notations as to what those are. So group 1, this column right here, remember those are the alkali metals. Okay. Alkali metals. Okay. The next column over, group 2, if you're looking at the numbers above the periodic table, okay, so this column, those have a similar name. Those are the alkali earth metals. Okay, and that's just sort of to distinguish them. We'll see a little bit later that they have a different charge and they react in a little bit different way. Okay, this whole area right here, okay, this middle section, I sort of left this out when we were at ptable.com, but this whole middle section here has a special name. These are called the transition metals. Okay, remember they're all metals. Anything to the left of the staircase, okay, and remember the staircase is right here, okay, so anything to the left of that, those are all metals, so transition metals. And then over here on the other side, we've got group 17 right here, okay, those are the halogens, that's an O, okay, and then the next row over to that, those are noble gases. Okay, and then down here at the bottom we've got lanthanides and actinides. Sometimes they're called lanthanoids or actinoids. Really, either one of those would be fine. And then remember that sort of in broad strokes, if we wanted to name this stuff. Okay, sorry, really hard to erase here on the little notepad that I'm writing on. Okay. So remember that if you look at the staircase, then there's some other ways to identify the categories. So if you look at the staircase, everything that touches the staircase, with the exception of aluminum really, okay, because aluminum really does touch the staircase. The staircase is like right there on aluminum. Aluminum's still a metal, but everything else that touches the staircase there is what we would call a metalloid. In other words, it's in between metal and non-metal. So everything to the right, non-metal. Everything to the left is a metal. Everything that touches the staircase is a metalloid. Okay? So remember those broad categories. That will just make life easier when we're trying to do electron configurations and naming a little bit too. So just sort of remember what those things are. And if you have any questions, go back through the video or ask a question and we'll make sure that you know all those categories. All right? Thanks, guys.